Welcome to all of our SVM 12th students. Today we are going to see about motion of a charged particle under a electric and magnetic field. Electric field can extract a electric force. Magnetic field can extract Lorentz force, magnetic Lorentz force on that charged particle. Due to these two forces, charged particles, first of all, separately if we apply, that can be deflected in its path. So how it can be deflected? That first we will go through that. Separately we will take an electric field, then we will see about that magnetic field, how the magnetic field experienced that extract a force on the charged particle. This portion is in our third lesson, magnetic effect of electric current. Anyhow, first of all we are going to take on a charge symbol going to take on as Q. Whatever may be that is a particle. So it has a mass. Then mass of the charged particle is suppose if it is in a moving, there we are saying velocity of the charged particle. Particle can be taken as V. So Q charged particle which has a m mass, it is going to move in a v velocity. Suppose now we have taken electric field, uniform electric field which has certain intensity, that may express as a E electric field intensity. In this electric field, Q charged particle, suppose moving along the electric field. If it is a positive charge, that Q charge is a positive charge, moves along the electric field means the particle, Q charged particle can accelerate it, because this Q charge can be expressed a force F is equal to EQ. Based on that force, that Q charged particle can accelerate it along the direction of that electric field if it is a positive charge. Suppose if it is a negative charge, what happens? Minus Q is taken means, first of all, if it is enters in a v velocity, that also can be expressed the force F is equal to minus EQ. Due to that force is acting opposite to the direction of that motion of that charge. So that's why that charged particle retarded, and at a certain time velocity becomes at 0 and turn back to moves in this path. So if it is a positive charge means move along the electric field, accelerated along the electric field. If it is a negative charge, accelerated opposite to the direction of that electric field. If we move the charged particles in the direction of the electric field means like that the particles are accelerated. That same charged particle in that same electric field, suppose moving some other angles, not along the electric field, if the charged particle moves some other angle, at the same electric field we are taken, Q charge is taken, suppose if it is a positive, and before entering that field, that is moving perpendicular to the electric field. After that, anytime if the charge is enters inside the electric field means that will experience the force along the electric field. Due to that, the positive charge turned in this direction. This may be taken as a parabolic path. If a charged particle enters with perpendicular to the electric field, turned moves in the direction of the electric field, the shape of the path is a parabolic path. Suppose if the charge is negative charge can be turned to moves in the opposite direction, because on the positive charge electric forces act along the electric field. On the negative charge opposite to the direction of the electric field, force is acting. But whatever may be that, the directions are opposite directions and moves in that parabolic path. Not only this perpendicular direction entered, for any other angle except 0 degree and 180 degree. In all other angles, if the charged particle enters in electric field, the charged particles can move in a parabolic path. So either straight line or parabolic path. When it moves in a straight line, if the charged particle enters along the electric field or against the electric field, charged particle can accelerate in the same straight line itself. Anyhow, if the charged particle enters other than that 0 and 180 degree, that the charged particles moves in a path, parabolic path. This is the movement of the charged particle inside the electric field. Next we are going to see about the same charged particle, Q charged particle, which has a m mass and moves in a v velocity, if moves in a uniform electric field. So we are going to take that uniform magnetic field, the same Q charge enters inside a uniform magnetic field which has a B magnetic induction. If the charged particle enters along the magnetic field, what about the magnetic Lorentz force formula means? We know that F is equal to magnitude BQB sin theta. Here theta value is equal to 0 degree. If theta 0 means sin 0 becomes a 0. F value is 0. If the same charged particle enters opposite the direction of the magnetic field at the same condition also, that F is equal to BQB sin 180. We know that sin 180 also 0. Then that also at the condition of 180 degree movement also force is 0. So we know that when charged particle enters in a uniform magnetic field, along the magnetic field or against the magnetic field, a magnetic Lorentz force value becomes a 0. Magnetic Lorentz force value becomes a 0. Other than these two angles, if the charged particle enters in a uniform magnetic field that can experience a force, we have a value. When it can be experienced a maximum magnetic Lorentz force, we have the formula F is equal to BQB sin theta. If theta is 90 degree, sin 90 becomes a 1, force becomes a maximum. So for 180 degree and 0 degree, force is 0. 90 degree perpendicularly enters means maximum force. So what shape of the path? According to our Fleming's left hand rule, we can trace that the charged particle in a uniform magnetic field can move in a circular path if it is entered in a perpendicular. So after that we will see other than 0, 180 and 90 degree, other angles if the charged particle enters in a magnetic field. Suppose charged particle enters in this direction. What shape of the path means the charged particle can be moved like this path. What is the shape of this path? Helix. So 0 and 180 degree, no force is experienced. If the charged particles enters in a magnetic field at 90 degree, then the charged particles can be moved in a circular path. Other than these three angles, if the charged particle enters in a uniform magnetic field, they can be moved in a helical path. These are the conditions, the movement of the charged particle in electric field as well as the magnetic fields. So now we are going to use both the electric fields at the same instant. Electric field and magnetic field at the same instant. Now for producing electric field, we are going to tackle here two parallel plates. These parallel plates are going to connect with a battery. Battery is one terminal is a positive, another terminal is a negative. If you connect the battery to the parallel plates and switch on that battery, means one plate occurs a positive charge. Another plate can be occurs a negative charges. So due to that upper plate positive, lower plate negative, what happens means electric field is produced in a downward direction. If that plus q charge with v velocity if we entered, in what direction it is entering? Perpendicular to that electric field it is entering. After the entering that electric field, the charge can express the electric force. That is a Coulomb's electric force that makes to move along the electric field. So it may be traced in a parabolic path. That is, downward force is acting on that charge. Downward force, electric force, E is acting downward direction. But we want to make the charged particle to move in that same velocity, in that same direction without deflection. We want to make to move the charged particles. So because of that electric force acting, that is deflect in the downward direction. The same amount of other force if you apply, that charged particle can move in a straight line. What kind of force we can apply for other force? Other force means we will apply the magnetic force, magnetic Lorentz force. We want to produce a magnetic Lorentz force in upward direction with equal amount. Then only that a charged particle can be moved in a straight line. So we want to produce a magnetic force in upward direction. The same amount as like that electric force. The magnetic Lorentz force we are going to produce. For the want to produce a magnetic Lorentz force in upward direction, we want to produce a uniform magnetic field around this region. What direction we want to produce means based on that Fleming's left hand rule. We will take on that. We know that definition of that Fleming's left hand rule. In our left hand, first three fingers are stretched perpendicular to each other. We know that first forefinger shows the direction of the magnetic field. Mid finger shows the direction of that current. Then thumb shows the direction of that force. So like that we want to apply. We know that the movement of the charge is this. And towards right that the charge is moving. Want to produce a force in upward. That's why in this region we want to produce a inward magnetic field. That the magnetic field can be adjusted by using an electromagnet. We can produce our required magnetic field because already we produce electric field fixed value. But magnetic field going to experience the magnetic Lorentz force. That magnetic Lorentz force value should be adjusted to equal to that electric force. So that's why here we are using a electromagnets to produce a uniform magnetic field and adjustable to make the force, magnetic force, Fm value, magnetic Lorentz force, this must be equal to that electric force. Then only the charged particle can be moved in a straight line. Then that velocity of the charged particle we consider V0 without deflection, zero deflection condition. The charged particle is going to out of our both electric field and magnetic field. So that's why here we are going to take an Coulomb force equal to magnetic Lorentz force. What is the Coulomb force on that charged particle? F suffix E equal to field intensity into charge. That value equal to magnetic Lorentz force. We know that formula for the magnetic Lorentz force is F is equal to BQV sin theta. Here theta value is 90. Sin 90 becomes a 1. That's why that is Fm. Then Fm is equal to BQV alone. The sin theta becomes a 1. If these two are equal, we can consider that velocity is a V0 velocity, zero deflection velocity. That is EQ is equal to BQ V0. Then we know that Q and Q cancel. V0 is equal to E by B. This is the one particular velocity for a given electric field and a magnetic field. That charged particle can be comes out with the crossed electric and magnetic field without deflection. Other than this velocity means that the velocity of the charged particle, if is changed, the charged particle either greater electric force or greater magnetic force at the time of equal only, that is electric force equal to magnetic force only, that comes out the field in a same without deflection direction. Now we are going to tackle three conditions. We required to produce a velocity V0 is equal to E by B. Then only without deflection that charged particle can be comes out. We can select that particular velocity charged particle in a straight line itself. Suppose our producing charge velocity can be considered as here V. This value either equal to V0. If it is equal to V0, V is equal to V0, our producing velocity is equal to V0, that value is E by B, then can move in straight line. We can say without deflection. The charged particle is moving. Another condition if you tackle, V is less than V0. What we are going to tackle means, if V is V equal to V0 means, we have the condition electric force is equal to magnetic force. If V is less than V0 means, magnetic force is less than the electric force. Which one is dominated here? Electric force is dominated. Coulomb's electric force is dominated. So that's why our charged particle can be deflected in the direction of the electric field because of our positive charged particle. If V is less than V naught. Our charged particle velocity is less than that V naught. V naught is nothing but a selected velocity. Our velocity is less than the selected velocity. Electric force is dominated and deflected away. That velocity particles are not taken out, that is deflected away. Another condition also we have, V is greater than V naught. Our charged particles velocity is greater than that particular velocity. So we know that magnetic Lorentz force formula, F is equal to BQV sin theta. Sin theta becomes 1, no problem. But V increases, force also increases. If force, magnetic force greater than that electric force, which one is dominated here? Magnetic force is dominating. So electric force is lesser, magnetic force is dominating. Magnetic force is dominated means net force act along the direction of that magnetic Lorentz force direction. So that's why can be deflected. In the direction of magnetic Lorentz force. Not in the direction of the magnetic field, magnetic Lorentz force direction, it may be deflected. So that's why from these three conditions, we can say the charged particles can be selected one particular velocity if you apply a definite electric field and magnetic field. So our arrangement should be two crossed fields which are right angle to each other, and that should having a particular value. Then that the charged particles are taken in a straight line itself. That type of arrangement is called as a velocity selector. Generally, the crossed electric and magnetic field means that the electric and magnetic fields are perpendicular to each other. If the two are perpendicular to each other, then only the two can be produced electric force as well as the magnetic force in opposite direction. Without deflection, the charged particle can be comes out. That is the principle of velocity selector. This velocity selector is used in mass spectrometers. Most familiar mass spectrometer is a Bainbridge mass spectrometer, because there we are taken that select the isotopes from all the isotopic materials. So particular velocity isotopes only we are selecting by using a velocity selector, which are having a crossed electric and magnetic field. So that's why velocity selector means we have here two fields, that two fields are act in right angle and produce a forces in opposite direction. If the two forces are equal and opposite, without deflection the charged particle can be comes out. That is the major principle used in mass spectrometers. Most familiar mass spectrometer is a Bainbridge mass spectrometer. Okay. Next we are going to see about one of the example problem. One of the example problem. What velocity it is comes out, then there if you apply a potential difference, what happens that charged particle, whether it is moves in a straight line or deflected in some angle. So what potential we required, we are going to see. Okay.